All right, I think I should be recording right now. All right, hello everyone and welcome. I thought I'd put together this really quick PowerPoint presentation just to go over some common AI terms and go a little more in depth. Maybe a live demonstration of Olama, maybe a little Klein, some AI assisted coding here this evening. So I guess the target audience of this little presentation that I put together is someone who is curious about AI, but they don't really know where to begin. I should preface this and say that I do use AI, but as a hobby, just as a tinkerer, just me being like frankly nerdy. But I really think AI is an extremely interesting topic. And I'm hoping that this presentation can at least like transfer some of that enthusiasm that I have towards anybody watching. So, this isn't intended for anyone who's an expert, but just someone who's curious about AI and they want to get a little more familiar with some terms and maybe see things like a little more complicated than an AI chatbot running on a machine. So here's the presentation. Without further ado, let's get started. So, demystifying AI terms, a beginner's guide to local AI models. All right, so why go local? Why would you use an AI or an AI locally when you already have tools like ChatGPT or Claude from Anthropic? Well, number one is privacy. Your data stays on your local machine. This is perfect for individuals who are working on an application that they intend to sell to others. This is perfect for products in development, and you don't want to expose your intellectual property to any malicious parties, any cloud hosting services. Basically, you want to keep everything as private as possible and just not expose your source code, effectively something that you plan on selling to would-be prying eyes. The second is control. Local AI allows for zero usage limits as well as zero fees. When running AI locally, as opposed to a Claude or ChatGPT, there is no pro or premium or ultra model. You are limited only by the hardware required or the hardware capabilities of your workstation, as well as your ability to supply electricity to that workstation. Next is very similar to item one is offline use. You can have functionality without an internet connection. So long as your workstation is able to power on and run the model, you can run these models indefinitely and create as many projects as you want without any bandwidth caps, without any token limits. This is again like very similar to item one here. And number four, more so people like me, you're just willing to experiment and tinker. You hear a lot of talk about AI in the news, about AI in the Wall Street Journal, and you just want to see like what exactly is AI capable of when I'm not using it for local chatbots. I want to see like what is it capable of actually building from scratch. So that's what I hope to demonstrate at least by the end of this. Give you guys a little real world use case of AI. All right, so moving on, we have the big three components, how everything will actually fit together. So you have the model, the AI mind. This is a large file that's containing all of the all of the learned knowledge that is to be applied. So this is where you have things like, if you hear in the news, ChatGPT 4.0, 5.0, you have Claude Opus from Anthropic, you have Qwen, GLM or Minimax in regards to open source models. This is what they're referring to, the actual file itself that lives on your workstation. Pretty simple. Number two, your hardware. Again, pretty simple. Your personal hardware provides the power and the memory for the model to actually run. It's literally just like running any application on your computer. Then we have the runner software. So this is a program that actually interfaces your computer's hardware with the model that you're trying to run. So sometimes online, these are referred to as LLM frameworks, large language model frameworks, and this is where you get tools like Olama, LM Studio, VLLM, etc. We're gonna talk a little more about Olama and LM Studio for this because, again, this is a presentation aimed towards beginners, and I believe that these two are not only the most popular LLM frameworks, they're also some of the most beginner friendly. And they're actually pretty well hardware optimized, as we'll see a little later. Moving right along, hardware requirements explained, the home for your AI models. So AI models love parallel processing. You might have seen online, so everyone's familiar with graphical processing units, GPUs. You may have seen online neural processing units or tensor processing units, NPUs and TPUs. These are all different kinds of parallel processing misspoke there. These are all different kinds of parallel processors that all work very well with different AI models. As a side tangent, a parallel processor is a computational unit that is designed for executing multiple tasks simultaneously by dividing large problems into small independent parts. So this allows for faster processing and improved efficiency compared to a traditional serial processor like a CPU, which will handle a task sequentially. The best analogy that I use for comparing the difference between a serial processor and like a parallel processor, like let's say a GPU, is a CPU, a serial processor, will take, let's say, a 500-page book, and if I ask it to find every mention of the word cranberry in this 500-page book, a CPU will go literally one line from page 1 to page 2, 3, 4, 5, all the way one line at a time until it reaches the end of the book looking for that keyword, in this case cranberry. A parallel processor, like a GPU, is the equivalent of taking that 500-page book, tearing out all 500 pages, and handing 500 different people exactly one page. And then you ask that group of 500 people, does the one page in front of you contain any mention of the word cranberry? So compared to a CPU, a parallel processor in this instance will have an answer near instantly. And you can understand why this distributed computing like this at the small scale lends itself towards being much more in favor of running things like LLM models. So hardware requirements continued, memory and specialized chipsets. So AI models can always operate best when they have ready access to fast memory. An AI can run on traditional CPUs and system RAM, but its performance will take a massive hit, as per the last example that I gave. Most choose to run local AI models on consumer-grade GPUs. So this is where you get the NVIDIA RTX 5090, 5080, 3080. So you have like 12, 14, 24 gigabytes of VRAM. The reason why VRAM is important for local AI for most people is because the VRAM, video RAM, is readily accessible by the parallel processor that's running your model. So in this case, the GPU running on a graphics card has very, very fast direct access to VRAM. So when using a local model, typically what people will do is they'll load that entire model into VRAM just so that it has the best path for processing available to it. It doesn't have to go through the processor to use system RAM. It doesn't have to rely on the front side bus of your motherboard to access system RAM. It has on-chip access to very fast RAM. However, what we're seeing more and more of in these coming years is more and more vendors are offering AI specialized hardware that feature quote unquote unified memory. So this is where you have Apple Silicon, recently AMD Strix Halo, and the NVIDIA GB10 chipset. So unified memory is a singular pool of memory that can be dynamically allocated by the workstation as either traditional system RAM or as VRAM, depending on what the application requires. So to use a couple examples here. So you have AMD Ryzen AI Max Plus 395 processor, let me say. Let's see here. So 395, codenamed Strix Halo, is a powerful x86 APU. So let's go down here. Here you go. With system memory options ranging from 32 gigabytes all the way up to 128 gigabytes of unified memory, of which 96 gigabytes can be converted to VRAM through AMD variable graphics memory. So similar to what's being mentioned here, unified memory, the memory is either system RAM or dedicated VRAM, and it's basically a sliding scale where it can be adjusted on the fly depending on what you're trying to run. Same goes for, here's the NVIDIA option, the NVIDIA GB10. NVIDIA has partnered with a multitude of different vendors. This is the Dell example, the Dell Pro Max with GB10, similar to Strix Halo. NVLink C2C, ultra low latency with 128 gigabytes of low power DDR5 memory. It's seamless data sharing between CPU and GPU, enhancing efficiency and supporting demanding AI models such as generative AI and large language models. And then here you're getting into the Apple Silicon equivalent. I've noticed Apple Silicon is very quickly becoming like the go-to option for off-the-shelf AI and large language tinkering. So here's the possibly like the best consumer option available from Apple. You have the Mac Studio with either the M4 Max processor or the M3 Ultra processor, the latter of which offers up to 512 gigabytes of unified memory. So again, it's both system RAM and video RAM. How much is system RAM and how much is video RAM is adjusted on the fly depending on the task that you're trying to accomplish. So when you're dealing with local AI or just AI in general, some terms that you're going to hear mentioned a lot are quantization, as well as the term GGUF. So what exactly does that mean? What is a GGUF? To put it simply, a GGUF is a very specific type of model quantization. This is essentially decreasing the quote-unquote resolution of a model's thought capacity, allowing for better efficiency to run on consumer hardware. So there are various other kinds of quantization, such as GPTQ and AWQ. However, you'll soon learn the more you research like AI topics, like watch AI-related videos and new articles coming out about new models, you'll quickly learn that GGUF is very quickly becoming the standard for model quantization. Another analogy that I can use to describe quantization is it's very similar to color bit depth in regards to video compression. I'm wondering how much sense this is going to make for people. But essentially, the core values of the colors are still available, but with a little less nuances. So here's a screenshot that I have, the difference between 8-bit color depth and 16-bit color depth. So you can clearly see with both of them that there's a clear distinction regarding what is red, what is pink, what is blue, what is cyan. But you can see that with 8-bit color depth, although there's less colors to choose from, you're still losing a bit of the nuance. You're losing a bit of the shades between pink and blue, between blue and cyan. It's very similar with quantization of AI models. So they still have that core thought processing ability, but you're losing a little resolution to its ability to think. I'll get into this a little later, but there are actually teams that have taken upon themselves to take existing AI models and just make quantized smaller versions as efficient as possible to try to get as close as possible to that original final output while keeping a smaller file size for consumer hardware. So let's go back over here. So hardware sizing guide, the model that you run locally on your machine depends greatly on your system's resources. So a rule of thumb is to basically take the download file size of your model and add about 10 to 15%. And that number should be the total system RAM that your machine has to comfortably run that model. For example, if you have 8 gigabytes of unified RAM or VRAM, you should target models that are under 4 billion parameters. So for example, you have Llama 3.2, 3 billion. Going up, if you have 16 gigabytes of VRAM or 16 gigabytes of unified RAM, you should be comfortable running 7 billion or 8 billion parameter models, such as Mistral 7 billion or Llama 3.18 billion. So all the way up to 256 gigabytes of VRAM and above. You have pretty comfortable support for models with over 200 billion parameters. A good example is Qwen 3, 235 billion parameter version. And let me see if I could, I'll pull this up a little later. We'll see if we could show you the actual file sizes of these different quants to try to put some visualization to what I'm describing. All right, so popular tools. So these are the LLM frameworks. This is the bridge between your machine's local hardware and the actual model that you're trying to run. So Ollama, I like to think of as the gold standard for beginners, or should I say serious beginners. It has excellent hardware optimization, excellent use of NVIDIA CUDA, Apple NPS APIs for very direct access to those, either the GPUs or those, should I say, those parallel processors on your workstation. Ollama is excellent. Same goes for LM Studio. It has a very intuitive graphical interface. It's geared a little more towards beginners, but it has some of those pro features of Ollama. It has a centralized UI for not just using your models, but for also downloading new models. You wouldn't have to search online for new models if you don't want to. That feature is actually built in. It actually has support for Apple MLX models. So as opposed to GGUF for quantization, you have also MLX, which is a model completely reworked just for Apple Silicon hardware. So just to show you guys here, yeah, downloading models for local use. Most user-friendly frameworks offer sites or tools within their application to easily browse and use desired models. So you have ollama.com/library and lmstudio.ai/models, as well as huggingface.co. So we'll explore those right now. So if you have Ollama installed, this is where you would browse by default, at least for some of your models. Just to visualize what we were talking about with quantization and GGUFs. So let's say here for DeepSeek R1, 77.2 million downloads just from this site. So notice how we have different parameter versions. So these are different versions of the exact same model. One is 1.5 billion and it goes all the way up to 671 billion. And if I click on view all here, you can actually see the file size here, and some of these actually show you right here. So Q4, so that means a quantization in 4 bits. Q8, same thing, a quantization in 8 bits. FP16 is the full fat uncompressed version, but this is the 3.6 gigabytes. So this is the uncompressed version of the 1.5 billion parameter model. So this goes all the way up to the truly uncompressed, totally unquantized, full fat version of DeepSeek R1. This is just one example. 671 billion parameters. FP16, no quantization, just the full fat model. 1.3 terabytes just in file storage just to download this, not even accounting for loading this into system memory for your parallel processing, NPUs or GPUs or what have you. This is where you're getting well beyond what is readily available to consumers, and this is when you're getting much more towards the $30, $40, $50,000 specialized NVIDIA hardware. So you can understand kind of why companies are at each other's throats for these specialized chipsets. Just DeepSeek R1, which is an open source model, requires 1.3 terabytes of storage, and then a little tiny bit more on top of that to load it into system RAM to actually run. So realistically speaking, if you're using consumer grade hardware and like you're building, like, let's say a small cluster, you would be using the Q4 quant of the 671 billion parameter model, 404 gigabytes. If you have a cluster of machines using either Apple Silicon or NVIDIA CUDA, you could probably get away with the 713. But again, this is getting beyond one specific machine. This is basically daisy chaining multiple machines together to share resources. Again, this is just Ollama. This is by default where the app will take you if you want to download local models for your machine. Same for LM Studio. So we have lmstudio.ai/models. So this functionality, at least if you're using LM Studio, is built into the application. You do not have to use the website if you don't want to, but this is just a visual to see. So let's say DevStral 2. Will it let me click on it? All right, it doesn't let me click on it. There we go. Okay, so let's say DevStral 2, you get a description, a little more details as to what this model is. DevStral is another open source model, again, here. So you can see that there's different versions of it made by the entity. So in this case, Mistral AI has DevStral Small version 2 and the full-size DevStral 2. So that's a difference between 16 gigabytes and 70 gigabytes. And again, the biggest difference is going to be actual functionality, actual parameters, and just how knowledgeable this model is. It depends on what you're trying to do and how complicated of a task you're asking these models to help you complete. I don't want to get too deep into the weeds. This is still supposed to be a beginner-friendly presentation. So let's move along. Okay, so huggingface.co, this is very similar to GitHub. This is a massive online repository for finding new models as well as fine-tunes and quants of existing models. The free account allows you to sample models via Hugging Face Spaces, as well as easily view model compatibility with your described hardware. So if I go over here to Hugging Face, so just to use this as an example, this is what I'm talking about in regards to quantized versions made by the community. So this team here, unsloth.ai, they don't directly make any AI model. All that they do is they take existing AI models and they have their own proprietary process of going one weight at a time and very efficiently finding which weights can be compressed and which weights should remain at full resolution. And actually here, if I say, let's say here, the Q4 quantization of Qwen3 coder, you can actually scroll down here and click on the individual weights, and they actually tell you whether or not the individual weight is compressed or not. So you can see here, blk.1.attention_k weight. So this, they were able to safely compress to a Q4 quant. And you can see here, this k_norm.weight, they found it more efficient to leave this at the full resolution, in this case, F32. Same for, you can literally go through here if you were curious, and you can actually see, this is all that this team does, is they take existing models made by other entities, and they basically review every individual weight, and they find out which ones are safe to compress to a lower resolution and which ones should remain at a higher resolution for better quality of output. Hugging Face is incredible for finding new models and different fine tunes of existing models. They also have a cool feature where you can enter the hardware specs of your workstation, and it'll actually tell you, okay, based on the hardware that you described, in my case, a MacBook Pro with 32 gigs of VRAM, or unified RAM in this case, these are the quantized versions of this model that you should be safe running. Yellow is a little iffy. You might have performance issues, you might not. Red is full stop. We do not recommend this. Your hardware is not capable of running this model. So I cannot run the uncompressed BF16 version of Qwen3 coder. I cannot run the 8-bit quant of Qwen3 coder. I can maybe run a 6-bit, but it's saying I'll be much more comfortable running something like a 5-bit quantization or a 4-bit quantization. This _KM_KXL, these are basically different methods of applying this level of resolution compression, if you want to call it that. So KXL is the more advanced, depending on what you're asking it to do and depending on your LLM framework, you may or may not be able to use KXL. I've had much better luck with KM and _1. These are older methods of 4-bit quantization. Same with, let's see, here you go. So Q4_0_1, these are very old methods of quantization. You have a slightly larger file size. So you see 19.2 gigabytes as opposed to KM, which is a little newer. They're all 4-bit quantizations, but these are newer methods of applying those quantizations. So you see you get a tiny bit of help in the file size. This also helps for memory. So yeah, I don't want to get too far in depth into this, but let's see if we can show you guys a live demo. Let's see what can be done once our tools are actually set up. As a disclaimer, since I'm running a live screen recording, I don't want this screen recording to be impacted by the resource usage of running a local language model. So for this instance, I will be using Ollama Cloud. It's literally Ollama, but instead of using one of my local AI models, for sample purposes, they allow Ollama Cloud, where you use their distributed computing clusters to sample new models, and that should be fine for this demonstration. Just know that local AI usage is exactly the same concept. It's just for the purpose of giving you guys like a very intuitive and drama-free stream. We're just going to use the Ollama Cloud model just so that there's no frame rate stutters or anything like that. So again, here are my notes. Why am I using Ollama Cloud? Because you're circumventing, privacy and all that. It's mostly because I'm currently screen recording and I don't want the performance impact to ruin the stream for you guys. And also because Ollama Cloud is currently free. It's literally free computational resources on their end for the purpose of reviewing and analyzing whether or not you like new models. So if they're giving you free computational resources, you don't even have to pay for electricity, no trials, no signups, literally just Give them your email, and it's here. Here's free computational resources. Why wouldn't you use it? I don't know. That's what I have to say about that. So going back over here, let's see if we could get this set up for you guys. So here is a connection to a Raspberry Pi on my local area network. So in this example, I have a music folder. Inside, I have an album from Daft Punk Discovery. I have the individual songs. I'm connected, as you can see right here, connected via 192.168.1.25. So let's go here to PiShare, and I have the folder called demo for you guys. So let's actually here, I already have a terminal open, so let's bring this over here. Let's clear the screen for you guys, and I already have Ollama installed, so let's run it. Ollama list. Give it a second. Bang, there it is. So we have Ollama running up here. We can open Ollama, but basically all that we're seeing here are the actual models that I have installed. So from Hugging Face, you can see the notation here. From the Unsloth team, again, I have a Ministrel version 3, the 14 billion parameter model. This is a GGUF 4-bit quant, 9.1 gigabytes on my computer. I also have from the Unsloth team Qwen 3 coder, 30 billion, active 3 billion instruct GGUF, also a 4-bit parameter quantization. And for the free computing resources, just for this demonstration, just to give you guys a nice clean stream environment, just to demonstrate what this would look like, once it's all set up with local AI. I also have a DeepSeek version 3.1, 671 billion parameter cloud model. Same for Minimax M2.1, also the cloud model. So let's go to VS Code. Visual Studio app would like to access the network volume. Yes, of course you can. Of course you can access that. So Klein here, getting right into it, is a extension for VS Code that allows you to pair your VS Code with an AI model that is running on your machine. So in my case, I have it paired to the Ollama API running right up here. And in this case, I am running Minimax M2.1 Cloud. So let's say done right there. So let's go right here. Let's go to our demo folder. Drag that right into VS Code. So here's our empty folder. We have no files, no nothing. All right, nothing up my sleeve. All right, so let's open Klein. Let's go. I have this on my other screen. Let's bring up the prompt. So here's the prompt that we're going to try. Please create a simple program in Python that will host a web server and allow users to stream all of the music in the subdirectories of the following path: home, Caesar, music. Please note that this Python program is going to be applied to a remote machine that you do not have SSH access to. The folder demo you see here before you is in the remote machine that needs the web server created. It is located in the following path on the remote machine. So home, me, documents, and demo. The web server should use TCP port 8080 for this task. Python 3 and Flask are already installed on the remote machine. We just require a .py program. Don't worry about testing via the terminal. I can handle that on my end and let you know if it works. So here's the prompt. Let's copy it. Here, let's actually, I think it might be a little cooler. Let's clear this. Let's SSH into our Raspberry Pi and enter my super secure password. Give it a second if I entered that password correctly, and I did. So let's clear that. Let's go to documents and then demo. And then you can see right here that it is blank, which is good. If we go back here and then go into music and then discovery. So these are the songs that we hope to share via a website once we're all done. So let's go to the home directory here. Let's copy this prompt and let's put it right here into Klein, which will pass it to Ollama, which will pass it to Minimax M2 and give us a result. It'll basically take full control of this remote directory that is saved on my Raspberry Pi that I'm remotely connected to. And if all goes well, we should be able to run this program right here for you guys and basically demonstrate whether or not it works. So here it is. It's going to take a minute. Again, I'm using Ollama Cloud for this. I don't want the performance impact to ruin the stream for you guys. So here, Klein wants to create a new file, musicserver.py. Task completed. Created musicserver.py, a Flask web server for streaming music from home Caesar music. Features, runs on TCP port 8080, recursively scans all subdirectories for audio files, MP3, WAV, FLAC, M4A, AAC, Vorbis, WMA, and Opus. Web interface with a song browser, search, and audio player. All right, so let's see what that actually looks like. So here's our SSH connection into the Raspberry Pi. Let's see here, uname-a if you don't believe me. So here, Linux Pi, kernel 6.12.58. Let's say, let's go to documents and see those bad boys. Let's go to demo. All right, music server.py. So let's go and say Python 3, music server.py. Let's see what we get. There you go. So starting music stream server on TCP port 8080. Music directory is home Caesar music, and it found 14 audio files. That's perfect. Access the server using this this web address. So HTTP localhost port 8080 serving the Flask app music_server. Warning: this is a development server. Do not use it in a production environment. Use a production WSGI server instead. All right. So here is the log, and Control-C to quit. So doing this live, let's open a new tab in Firefox and let's go to HTTP 192.168.1.25 and port 8080, which is my Raspberry Pi. And there you go. Here is the music streaming server that is running on my Raspberry Pi that I am connected to from my local area network. So let's say I want to play one of these. I can't play the whole song for you guys. I'll just play the first couple seconds just so that you get the idea. One more time. I just want to hear that part. All right, you get the idea. I don't want to get copy striked by Daft Punk and then killed in my sleep. But here you go. That's the demonstration of Ollama running on an Apple MacBook Pro. Normally, this would be local AI. For the purpose of demonstration, we use Ollama Cloud. Yes, I know it's not really private or anything. It's just a demonstration. Give me a break. Okay, so live demo, operation successful. Let's move on to some closing thoughts and then I'll let you guys go. So closing thoughts, AI as an industry is massive and only getting bigger. AI is the first new technology in quite a while, honestly, that has made me extremely excited for the future and to see just how far businesses, nations, and communities will take it. It truly is a really, really incredible rabbit hole to fall into. I'm not just saying that. It really is like absolutely like mind-boggling. Like the more you look into this and the more that it's capable of. Once you move past like regular, like help me write a chicken, like a fried chicken recipe, or help me bake a chocolate cake or anything like that. Once you actually start giving it more access and like more permissions to actually like help you accomplish tasks, once you start looking at it more as a personal assistant, like a personal like a partner in crime, so to speak, it really is incredible just how far people are pushing it. This is a very, very small portion of what it's capable of. This is just a beginner's introduction to common terms. There's a constant stream of closed source and open source models that are being released in a very, very real arms race between the United States and China, competing for adoption and application of different AI models. I do not think white-collar jobs are going to disappear, but they will definitely be molded in favor of people who are able to better utilize AI models as well as their capabilities for workflows at hand. I don't want to take up too much of your time. This is really just to try to transfer some enthusiasm to get some people more excited as to what's actually possible with AI, especially local AI. Again, guys, like search engines are your best friend. If you want to know more about something, honestly, dude, to be completely honest, you can use AI instead of Google. You can use ChatGPT and enable web search and literally just ask it any question on a topic and just put at the end, please provide sources to back up your claims, just so that you get some web URLs that you can click on and just so that you can confirm that it's not making stuff up. Like it's an incredible resource for learning, for accomplishing tasks, for getting work done. As far as like hobbyist home labs go, like this is absolutely game changing. I don't have a crystal ball. I don't think all of my predictions will come true. If someone were to ask me where I think AI is going, I do not think white-collar jobs are going to disappear. But I do think white-collar jobs are going to change, and they're going to be more AI-centric. Again, thank you all for your time. Thank you all for watching, and I hope you guys have a great day.